The two teams that got injured after 3 injuries, one was UVM. She was supposed to grab the outside. And then 2 people from ESF that are SUNY environmental check. They're like basically right next to Syracuse. They're basically Paul Smith's like that. Like they got first, second, third.
That's school summer. That's not a college.
My sister went to Paul Smith's.
It's like all I ever hear about is like they're like spring and it's like
Because like specifically, there's 2 programs. There's 3 programs they offer. Forestry.
All right.
Firefighting. Culinary.
We're back.
Yeah, I did at some point. I think they might have done anyways, dynamics.
Last time on dynamics, we're finishing up the kinematics of like as we're driving this car jack, like moving the screw at a certain speed, how fast is everything else moving? So we've got rotation speeds, we've got linear, like pushing the car up speed. So the last question we left off with was, if I'm moving the collar down the screw at 3 millimeters per second, how fast am I raising the car? That was where we left off. So first question is, if I move the collar down the screw, will the car lift off the ground? Will it lift higher? So screw turns, collar moves. It's got to go up because it's all 1 degree of freedom. So if I say this thing has to move, everything else has to do whatever it needs to keep up with my screw. So then the next question is how fast? What is the connection between those two? Do we know? I know everyone like ran home and started scribbling notes to be like, oh man, I can't wait for Monday. I'm gonna blow everyone's socks off with this equation that I just found. Maybe? For VB, yeah. Tan theta? 0.006. Okay. Why do we have that? I'm gonna put why would it be this? Does that make sense? Yeah, where did I get that? Anyone know? What do we think? Did I already talk about the magic arrow? Do you know the magic arrow? That's what we used to use in grad school, of like, we know the math equation works out, but we have no idea how to get from this to that. So you just draw an arrow with a magic star next to it, and that kind of explains where the math came from. So magic arrow. Can you fill in the magic arrow and make it less magic? Where did 6 tan theta come from? And we can turn this into like, I just like millimeters instead of meters. What is that? Do you know where, like how to get there? Yeah, yeah. We can take that ratio, the whole vector. The I component. Yeah. Yeah, that makes sense.
I'm just going to keep the arrow star for now.
This here, we're given that this here.
No exams. Plenty of classes that give exams schedules that don't use them. I had 5 exams equal student body class.
3 millimeters. Right, that's what we're beginning. So then,
Yeah, it doesn't give us like the but it does tell us.
theta dot, sine of theta. This is something we don't know, right? So this is just we can replace this into this, and we turn this into cosine.
I was at the pre-exam classes.
Which we can do that by
I'm sorry, I didn't do it during
equals sine of so then sine times so then
I have no students, I have 3 in-person classes.
So I just have to be really good. And then that's not
Within mechanical science. Well, they're on the 4th and the 5th month.
All right, you ready for some fancy math? Filling in the magic arrow, like how do you get from one to the other? We have 2 equations with 2 unknowns. I don't know VB, and I don't know theta dot, but I have 2 equations that I can solve for them. Take them both, divide them. Does it depend on the length, like how long these things are? Like if it's 20 centimeters versus 10 centimeters, is it going to move faster? No, the L's cancel out, right? Theta dots also cancel out. It's another unknown, but at least from this equation, I don't need to know how fast it's rotating. I can just cancel it out. So it's at 2 VAX times tan theta, and that's how fast we're moving up. So if I'm moving my little screw at 6 millimeters per second, then the car is moving up at 12 millimeters per second, at least when tan theta is 1. Or sorry, 3. We had 3 and 6, my bad. All right, so now let's do a check. Tan theta is 1 when theta is 45 degrees. So that's when we have what is tan theta at 0 degrees? This one's tricky, yeah.
It's when sine 0 is sine of 3.
Yeah, so it's sine of 0 divided by cosine of 0. Sine of 0, 0. What about 90 degrees? Undefined? It's defined. It's defined.
It makes a tangent graph.
It does make a tangent graph, yeah. So we have like an asymptote at 90 degrees. Something, not a great drawing. That's why I prefer doing,
All of those things.
Yeah, so technically, the velocity approach is infinity.
Oh wait, that's cool.
Technically.
so it's not, yeah, technically as we get closer to 90 degrees, for 1 little millimeter screw, we're moving the thing up at an infinite, so 1 millimeter per second is going to have an infinite millimeter per second upward. It's really small though, like this is, and it's at the upper limit of how high this thing can actually travel anyway. But it's good to think about these kind of kinematics, because like if, right now we have a screw-driven thing. If you're driving something with a screw, it's very stable. But if you were doing like piston-driven, like pushing with a piston up to 90 degrees, you're probably going to have like a pop-through event where the car jumps up, the thing folds in on itself, and then slams back down. So it's good that's why we start with kinematics first, just to see like, is there anything weird happening as we're trying to say, you go this way, you go that way, and everything else, do whatever you need to. Because sometimes you do get infinite motion, infinite like speed for very small inputs. That's okay. We'll get through it. And the nice part here is we did all the hard work to have like an actual equation. So even if we want to change what that screw driving rate is, we can change that. Like we can plug in a new number and we still have a way of calculating it. Cool? Seems cool. I think this stuff is cool. That's why I'm here. Never left. I just stayed for more fun stuff like this. All right, I'm scrolling back up because we can move on to step 2, looking at the kinetics. It's always good to look at moving components, start with kinematics so you understand the motion, then move on to kinetics and figure out how much force does it take to maintain that motion. So that's our next step. What are the forces involved so this thing doesn't like fall apart? How do we do that? That one, just shout it out. How do we do this? Oh, not kinetics, although kinects are pretty cool. How do we find the kinetics of this structure as it's moving? What forces we need? Maybe even on a body that we care about. Maybe we could draw some kind of diagram to represent it.
Free body diagram.
Maybe even a free body diagram, something like that. I know it was a little heavy-handed, but Mondays, am I right? Roughly a quarter of the car, we want that plate to hold it up. Then this thing comes down. We got a hinge over here, comes down again. And let's leave it like that. I don't like the way. All right, so I'm starting this thing to give us a starting point. I want you to finish it. I drew in the external, I drew the car as an external load. Like it's applying a quarter of its weight down onto our car jack. I also drew the screw as an external load. It's not external to our system, but I'm taking it away to see, in order for this screw to work, how much load does it need to carry? So I took it away and just replaced it with forces pushing inwards. What other forces do I need? How else is this thing? Yeah. At all the hinges?
I think so.
Okay.
This most can cancel out.
You think most cancel out? Okay. So hinges have to have some kind of reaction force, right? Because they're preventing motion. And anywhere you say don't move, there's a force applied. What's the... Sorry? And normal? I like normal, yeah. Something's normal here at the base. Okay. Some reactions. All right, so give it a shot. We know the hinges are creating some kind of forces. We know the ground is supporting it somehow. Like what's going on? What else do we need in here?
I think we're doing external. I think she just said the force is external technically, but it's
Are we including friction forces at all? Are we including the friction of the torque returns?
We should try to bring it together.
I agree. Let's do friction.
Let's do frictionless,
Steady inward pressure.
rigid bonds. Rigid bonds. We can't actually prove it's only a loosen like. To be clear, I messed with some setting. I messed with my setting. I was so close to brain dead tires. I was 9. It was supposed to be I got a 9. I was probably going to try on so I should laugh. A little different. I finished my 5 minutes and decided I'm going to price friends. I didn't even push cheat sheet. It was a waste of paper. Oh, yeah. Ice cream board?
That's what she did. No, I was such a little
So there's
So I was like, oh yeah.
Well, this is a reaction to it.
how perfect is our world?
Dividing it plus 4.
What is dude, it's mathematically, we just go outside.
That's what ECT says.
I think we changed the number.
What?
I think we changed
We just go carjack the cars outside and go switch outside. I'll leave that up to you. Do you rather steal someone's house?
Depends. If they have a line. Do they have a line legally?
Let's go some time so I go plug for a phone call. Well, no, I messed up one, so we can get money. Like, we can go do it.
Yeah, we definitely need to react.
Just search you. Let's go
That doesn't say
keep the steps.
scientific
My mom passed in New Jersey first. Just me like this. Walk down the tree.
We have a good amount of symmetry going on, so I'm not. Normally, I would have different, like, whatever, an A and a B reaction force, but here I can say RY. Then I could also do like some kind of RX and RX, right? Do I need other forces, like at the other hinges? They're internal, yeah. So, and that's one thing that I was trying to figure out here with this exercise. That difference between internal and external forces. So the reason that I'm drawing those forces at the bottom is because I'm not considering like a whole base plate. I'm not just saying there's like one big force from a base plate below. I'm saying there are hinges connected to something. So they're external to those hinges. Versus like the hinges over here, 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 and here. All those yellow hinges have internal forces that they're there, they're very real, but they're not external. They're not drawn on my free body diagram because it would just be add one in one direction, subtract it in the other. Kind of makes sense? How does it look? Can we solve for tension now? Yeah.
Would you have to look at internal forces to find the tension?
Okay. Which internal force? Why is that?
Because there's no external forces in the x direction.
Oh, all right.
Convert them.
Yeah, so I'm putting down a completely vertical force, but asking how much horizontal force there is. Sorry, go ahead.
Doesn't the vertical force have a component that is normal to the lever arm on the hinge?
Normal to lever arm.
Couldn't you like use a moment equation with the component of tension of the screw and the weight force? Or no?
Yes, we can definitely use moment. So if we, excuse me, let's do this. We'll do another split. What is this? Right now, we have 1, 2, 3 unknown forces. How many equations can we make with, like, Newton's laws? 3? 3? Yeah. So we can get 3 equations, but the one point that was brought up is that we might end up in we might end up with some kind of problem because there's like the thing that we know is perpendicular to what we're trying to solve for. Yeah.
I still think we need to break the vertical force into components based off the theta of this piece of supporting.
Yeah. How do we know that it's what the angle of the force is based on the supports?
Whatever angle they are at in this orientation.
Yeah. Is that always true?
It changes as the angle changes.
It'll change as angle changes. You know. So if we know the angle, so in this case, what we're kind of saying is like, we're saying the angle's going to change. So at any point, we can say we know it. Like we could solve for it.
So we need a function.
Well, the function is kind of like going from 90 to 0 as we're like folding up. So we'll probably have some kind of same for the velocity. Like we had ended up with a tan theta, probably have some kind of sine or cosine in there, right? But the question, but it was a great point of, can we Um, Can we say like the resultant force has to go through that object? Yeah? So you're definitely correct. The only time that this is not true, for anyone that's wondering why I'm asking, would it not be true, is like if you have something on a hinge that's at an angle, it's at a bracket, this thing, if I make a cut here, there can be a moment applied at that point. The nice part about hinges in our case is that a hinge can't create a moment, so all the force has to be along whatever is supporting, whatever the hinge is supporting. So we can use that as an extra set of like geometric constraints on our vectors, that if I know the orientation of my beam, then I know the forces all have to line up along that beam. Which is a good point, because in my free body diagram, I didn't include this guy, right? Call it like some kind of FX. As I split it, I like, the hinge is still a hinge. It needs to be able to support X and Y, which does introduce number 4, unknown number 4. So what do we think? Is it solvable or just no way? If I know the force here, $300. Like roughly 3,000 newtons. Can I figure out that tension? Do you think you can? Three equations, 4 unknowns. Impossible. Another constraint. We can use that constraint. So there were 2 things that were brought up. One was either split this up into more free body diagrams. You'll introduce more unknowns, but you'll get more equations. And it does work that way. The other option is using the geometry that we know, that the resultant forces all have to match the geometry of the structure. Both of those are equivalent. They'll end up with equivalent ways of getting to a relation between force at F/2 and tension. Other question here, what is the sum of the forces equal to?
Well, isn't that the stationary 0?
But it's moving.
Well, is this when it finished lifting or while it's actively lifting?
While it's actively lifting. This is actively moving.
It's going to be equal to the acceleration upwards times the mass.
Acceleration times mass. Yeah. So they all equal, so all these equal MA? We haven't really covered that last one, but moment doesn't equal like, haha, a push. Moment is a twisting, like a rotation, change in rotational inertia. All right, I'm gonna give you the vocab word that saves a lot of work. They're all equal to 0. Or wait, quasi-static? Yeah. So quasi-static analysis, meaning yes, this thing is moving, but the change in momentum is either negligible or it's really small. So somehow changes in momentum are really small. We're talking about trying to raise this car at a few millimeters per second. How many millimeters per second squared things are moving is basically 0. So it's a quasi-static analysis. So everything's just equal to 0. It's still moving, like it's still dynamic analysis, but we don't have to worry about like what is the rotational inertia of this thing, of these like moving parts. Question?
I was just gonna say, like, as the screw gets shorter and shorter, the car is gonna be lifting faster.
It is lifting a little faster,
So in
yeah.
theory, it is accelerating.
Yeah, once we get to the top, right?
And it's so negligible it doesn't matter. That's why.
Oh, yeah, it's probably going to be moving still pretty slow because we're still, even when we're saying like it's infinite compared to our screw rate, it's probably going to be like, I don't know, 100 millimeters per second instead of 6. So it's still not moving the car all that fast. It might change a little bit, but at least for first approximation, it's a good analysis to start this way, quasi-static. And gets people off your back because you thought about it and you made an executive decision. Back off, man. It's quasi-static. I'm a scientist or engineer. So what is that screw? How much load is it carrying? Give it a shot. See what you can come up with. Splitting it up like you had suggested, or just being it all in one? Okay, yeah.
G-screw, if you're using a split G-screw, that maximum or highest tolerance by itself.
Okay, yeah.
It's really opposite direction because the resulting force has to fall geometry.
You just put it on the top right. That makes you have 4 reaction forces, and tension says 5 unknowns, but it's at the moment equal to bottom.
You can solve for effects.
I mean, in terms of like, this is the pretty cool comment. Where's the line?
Yeah, I guess for some.
Just look inside, there's the compression force here. So what about the left? Carrying a lot of compression. Even if you cut that, you just have compression. We don't have to just. If you take the moment of this joint here, you can ignore this and resolve it. Well, any moment that goes through, any force that goes through,
But if we
and it over zero. But we, because it's defined by the geometry, all force needs to travel on that. Do you remember in Podcast 1, just where we're doing frame analysis and cut it from figure out. Yes. If you cut that, now you already have a compression force going on the way. And now it's a force that goes directly through that point, which means at the moment is zero. But it also goes directly through that point, so that's also if we're taking the moment about 20, you only do this. If you're taking it all the way, all the way up, taking that point, touching to that, except also the results of force is also. But we can calculate what the force is to get the case of the line to that. This is going to increase so this just come back to this. Not a six.
That's really part of it too, is like, you have to pay them taxes.
Yeah. Oh, for having some time.
It's just like you just use something. So you're telling me.
You have a business course?
No, I'm a business. Ah, fuck.
I mean, it seems like you're really good. You get paid for money. You get paid for music. You're going to work one job, you're going to do that.
All you need for
You're
it.
going to stay there.
Yeah, that's just really way, but also there's a lot of ability here. So. That's what I'm saying too. So okay, so I'm really close to that. I want to do more. Okay, so I'll be equally trust. Do we manufacturing good by chance? You can. Which one did all that? Sure.
How we doing? We got a couple minutes.
They do a lot.
You convert R to RY to tension and then it has to in.
Oh, I thought I was getting help. I'm like, yeah.
So they just like sit, like you sit there question.
Oh, because you click the bottom and just click.
I put this in the wrong spot. All right, so one thing that we know from this is that we can't use hinges to change how much the ground is supporting. If we're lifting a quarter of a car, we need the ground to support a quarter of a car. Doesn't matter how complicated the mechanism gets. That one hopefully intuitively kind of makes sense. Same thing, like if you lift a weight, and the ground has to support you and the weight, no matter how awkwardly you lift it. What about our FX? Here we have like a RX minus FX minus T screw is all 0. Did anyone try the moments? How much moment we have? No? Mystery for next time, I guess. How do we find like some of the moments? What's the first step? Yeah, pick like some point where we're calculating what the moment is actually being calculated around. Any preference? Which one?
at this point.
Yeah, the bottom maybe. We could call moment around O, right? How much of a moment is the car creating around O? That F. The F over 2, how much moment does it create? 0. Yeah.
Aren't you missing the vertical reaction force on the top hinge?
Vertical on the top hinge. Yeah, do we need that?
No, it's not. F over 2 is the force to the car. The reaction
Yeah.
force to the hinge is its own reaction.
Yeah. Do we want that? I think the main thing is that the hinge is holding the force of the car over 2. That the vertical force has to be F over 2. But it's a good point. Like the hinge is the thing holding it. The car is not directly putting that weight there. Yep. So really it was like to get to this was a 2-step process. One, I did a free body diagram. In my free body diagram that I have a plate with a load in the middle, 2 hinge forces up, 2 hinge forces that way. So there I have F over 2 vertical hinge forces down, kind of like that, and then get to that last step. All right, so we'll do some of the moments next time. Maybe we'll make some progress. Maybe we'll try something else.